Hi everyone, my name is Corey Adams. I am a staff scientist at Argonne. I'm a joint appointment between the computing division, so the leadership computing facility, as well as the physics division. So I'm going to talk to you today about a use case of machine learning in science. This is a project that I work on sort of jointly between physics and computing, so it's a really fun project for me, to be honest. I've got a lot of quantum mechanics and statistics and calculus in here. Can anyone raise your hand if you've taken quantum mechanics sometime? All right, so some of you will at least be following that. Everyone else, please ask questions as we go. So jump in. If I don't see you raising your hand, just call out to me, please. I didn't do this work alone, of course, so I've listed some of my collaborators here. And a lot of this is built on a lot of foundations from Monte Carlo simulations and statistics since even the 50s and 60s. Okay, so my talk today is going to be largely about nuclear physics. Why nuclear physics? What makes that interesting? So this graph is basically a plot of all of the atoms we know. And you know, it's really a plot of nuclei, but nuclei and atoms are kind of interchangeable. You just add electrons to a nuclei and you've got an atom. Everything in black is things that are stable. And here the x-axis is the neutron number and the y-axis is the proton number. So if you remember from physics classes, put together some protons and neutrons and you've got a nuclei. Of course, protons and neutrons themselves are composite particles. They're made of quarks and gluons. And quarks and gluons are governed by strong interactions, predominantly. They also experience all of the other interactions, but the aptly named strong interaction really dominates. And there's sort of a question in nuclear physics. How do you take this fundamental theory, quantum chromodynamics, that tells you how quarks and gluons interact, and go from there to telling you about the properties of a nuclei? It's a big reduction in phase space and dimensionality, and it's kind of a limit of QCD. But that topic of understanding the basic properties of nuclei is something I'm going to talk about today. At low energies, which is typically where you find them in a nuclei, the quarks and gluons are confined. That means they're all bound up into a proton or a neutron, or this particle called a pion. If you haven't heard of them, pions can be thought of as kind of force exchange particles in nuclear physics. So when a proton and a neutron bounce off each other, they might exchange a pion. Kind of like electromagnetism waves are the interactions of light and also electricity and magnetism. We can approximate quantum chromodynamics with what's called effective field theories. And what that means is instead of worrying about all of these complex Feynman diagrams in quantum chromodynamics where you have quarks and gluons and all sorts of complex interactions, you reduce it down to just a couple fundamental approximate interactions. So here, this is called the pionless nuclear Hamiltonian approximation. It's an effective field theory, and we just have two things to worry about. We understand when two particles bounce off each other, how they might interact, and we understand when three particles bounce off each other at the same time. So these two diagrams are basically simulating that. On the left, two particles come together. Somehow in green, quantum chromodynamics happens. We don't worry about the details here. And then two particles come out. And it's given by this potential term here, V. That means a potential energy, which is just dictated by some constants, C1 and C2, as well as these functional forms, V. And it's a function of the distance between the two particles. And this sigma term is about spin and isospin, which is just different configurations of the particles. The three-body term is really similar. You're using the same functions, but it's cyclic now over all three particles coming in. And these constants here we fit to experimental data. So even since the 50s, 60s, scientists have been able to bounce a proton and a neutron off of each other. And so we can measure this type of constant here. And on the right-hand side, this D term, well, that's based on the binding energy of tritium, helium with an extra neutron. Hydrogen with an extra neutron. That's a three-particle nucleus. We know what its binding energy is. That's its ground state. So we can measure those terms as well. The hard part about nuclear physics is it's a many-body problem. So in principle, you can write down the equation you need to solve just up there on the left. This is the Schrodinger equation, where you have some wave function, which is representing the state of all of your particles, basically the probability that you'll find every particle at every different location. And it's this operator equation. So H is not a function, but an operator. It has this potential term V, and it has this momentum term, kinetic energy, which turns out to show up as a second derivative. Things that solve the Schrodinger equation are eigenfunctions of H. So you take this operator on your wave function. If you get back your same wave function times a constant, that's a solution. Unfortunately, the exact solution when you have many body problems is exponentially hard. So the wave function is, I wrote it as a function of r, but that r represents all three coordinates of every particle, and then they also have spin and isospin coordinates. And as soon as you get to a couple particles, that starts to become computationally intense. You can do it exactly up to about 4 to 6 nucleons. If you want to go beyond that, you cannot solve it exactly, not on today's computers. So what I'm going to talk about today in this talk is methods to solve this equation approximately, though we have quite good results. And we're targeting nuclear many-body systems, but you can kind of extend this to any many-body quantum system. All right, questions so far on the nuclear physics? Yes?
What is the drip line in that first diagram?
Which one? This red line here?
Yeah.
So if you look at the labels here, the black are the things that are stable. Yellow are things that are known, so an unstable nuclei that maybe you could make in an accelerator. And I think this green might be unknown nuclei, so things we've never made. Okay. All of these techniques are based on this concept of variational Monte Carlo. There's a principle in quantum mechanics. It's really cool. It's called the variational principle. So you take any solution that you propose. It doesn't even have to be a solution to the equation. And you evaluate this quantity on the right. This is called an expectation value. It's basically a way to take that operator h, apply it to your function, normalize it with this denominator, which is just telling you what's the total strength of your trial function. And whatever value you get out, you can prove mathematically in quantum mechanics that it is higher than the ground state energy of the system. And the ground state energy of the system is the lowest state. So if you have a hydrogen atom, the electron's in its lowest orbital, that's the ground state. If it gets excited, gets bumped by something else, that's not the ground state. Any trial wave function you try on the hydrogen atom is going to have at least this expectation value of its energy that's higher than the ground state. So for bound systems, so things that are pulling together, that's typically a negative number. If you have some of the artificial problems like the harmonic oscillator, where your potential goes to infinity at infinity, that might not actually be a negative number, but it's still bound. Here's the cool part. You pick any function that you can write down, and you can make it a function of parameters, so theta here. So r is all your coordinates, theta is some parameter. So if it's an exponential function, it might be e to the minus theta x. You can take this value, e sub t, and differentiate it with respect to your parameter. You know that whatever you get out is going to be still greater than or equal to the ground state energy, no matter how you change your function. So you can minimize that quantity. This is stochastic gradient descent, which you're all familiar with from machine learning maybe. You take your trial function and you keep applying this update until you get to some minimum of your function. For simple problems, you can solve this exactly. So if you try this on the harmonic oscillator with something that looks like the right solution, you're going to get the right answer exactly. For complex problems, often this turns out to be impractical to get to the best possible answer. You have to make a wave function, trial function that's so general, that has so many parameters and is so computationally complex that you can't always get to the best energy. You can minimize it, but you might be above the experimental energy, for example. Okay, a comment on this computation here, so E sub t. It was written, it looks somewhat simple on the right-hand side here. This is the reality, so it's a bunch of integrals. The denominator is integrating the wave function over all of space, and it's actually the wave function squared, the absolute value squared. In quantum mechanics, that represents a probability distribution. So that's something of a normalization. On the top, you have the same thing, but with this H operator sandwiched in between. And that is letting you calculate the expectation value of the energy. But remember, it's an operator, so it's operating on that second psi sub t. And this R here is really the challenge. So if you had just one dimension, the harmonic oscillator, this is super easy. You can do this on your laptop. You just pick a bunch of points, trapezoid rule, do your integral, you're done. If you do this for a giant nucleus, you have 3 times n particles dimensions to integrate over. You cannot just scale out your grid search for your integral. It doesn't work. You would need more memory than we have available. So we don't do that. We don't even try to do that. Instead, we use a statistical technique from the central limit theorem. So this is a lot of statistics. There's a lot more detail in some of the backup material I have linked to later. We don't have to go through all this in detail, but basically the point is, if you have an integral down here, I equals dx of some function, you rewrite it like this, where you've just multiplied and divided by some function p of x, where p of x is a probability distribution. So if you draw your x samples from your probability distribution p, then the value of this integral can be computed just by summing. So it's basically this summation on the top. And if I take our expectation value energy, rewrite it a little bit with this E sub L term, which is this H operator on the wave function divided by the wave function itself. This whole integral, you can show, lets you write this in this form, where you've got this probability distribution on the top, your normalization on the bottom, and then E sub L. And if we sample R from the right probability distribution, we just compute E sub L for every R we've sampled, sum them all up, and that's an approximation of our integral. In quantum mechanics, this term here, psi tr absolute value squared, is a probability distribution. So we've taken this multi-dimensional integral and backed up a step and said, if we only knew how to sample from this probability distribution, it's no longer a multi-dimensional integral. It's just a summation over a couple thousand, 10,000, 100,000 points. If you have a GPU, that's easy. How do you do it, though? How do you get your values to come out? And just to point out here, not only can you get the expectation value of the energy, you also get an integration error built into this theory. So the way you get to this is from this algorithm that's, I've written here, MRT squared algorithm. It's named after some people, Metropolis, as well as Rosenbluth, Teller. This is from the 50s and 60s. It's basically kind of the birth of Monte Carlo sampling techniques. I'll talk through this a bit. In some of the backup material, there's a much more detailed derivation of how this algorithm works. You're going to see it if you do any sort of Monte Carlo simulation. You'll see things like this show up all the time. So you want to sample from a probability distribution. What you can do is start with some initial distribution at the top. And you just take a bunch of points in your space. So my space here is 3-dimensional coordinates for n particles, plus they all have a spin and an isospin. And my probability distribution is my wave function squared. So I have a trial wave function. It's a function of all of those particles. If I have some input particles, I plug them into the function, and I know the probability distribution to some normalization. So this algorithm actually lets you get away with that. You're going to be computing ratios of probabilities, and you don't need to know the normalization. For every particle, you apply some change, some small change perhaps. Typically, a common one is a Gaussian kick. So in an n-dimensional space, you get an n-dimensional Gaussian, and you add it to your initial particle. So that moves you from, say this particle to this particle. Some of them maybe will get moved, and some don't, based on transition probability. So after you apply a move, you recompute your probability. And you only know it up to a normalization, but if you take the ratio of those two, you can know if you're moving to a higher or a lower probability state. If you're moving to a higher probability state, this algorithm says just move. Don't look back, just move that particle. If you're moving to a lower probability state, then there's some acceptance criteria where, say, the ratio of the probabilities is 0.5. Then you have a 50% chance to move. If it's 0.9, you have a 10% chance to move. If it's 0.9, you have a 90% chance to move. 0.1, 10% chance to move. And what this does in the long run is all of your particles will generally flow to a higher probability state, but there's always a chance they're going to go to a lower probability state. And this lets you sample your whole distribution, even getting into the lower probability corners and tails and all the little valleys. And in the long run, after a large number of these iterations, you will have a sample of points that is drawn from your probability distribution. And that's a probabilistic fact. You can prove that with statistics. Questions there?
When you say the final result is coming from the probability distribution, is that the same as the initial distribution?
No, and in fact, it's really cool. You can prove that the initial distribution does not matter. If you run this long enough, you will get to the probability distribution, and it doesn't matter what your initial points are. Yeah, go ahead.
Does the convergence of it depend on the number of bodies, so again for the n-body problem?
It doesn't necessarily depend on the number of bodies you have, but it does depend on how much your probability distribution is changing as a function of those, so it's kind of a second order effect. The biggest two things that affect the convergence is how many iterations you do and how big your kick is. So you have to tune it, actually. And there's lots of papers that say, if your tuning is this, you're not going to converge, and it's a little bit finicky. People still use it, though, because it's kind of a miracle that you can take any function that's a probability distribution or like one and sample from it without knowing the full distribution. Okay, this algorithm has some nice and some not nice properties. So the nicest thing is, by far, you can sample any function. And each iteration, computationally, just depends on how long it takes you to evaluate your function. So if you have a really complex function as a number of particles, it's going to take you a while. If you have something really fast, this will go really fast. It's also conceptually, numerically, and analytically simple. Right? You're just doing this iterative step where you move to a higher probability space most of the time, sometimes to lower. And it's easily parallelized. So this is a type of thing that you can vectorize easily on a GPU. The downsides are it typically takes a while to converge, especially initially. So your initial distribution doesn't matter, but if you have a bad initial distribution, you're going to take much longer to get to a point where you've drawn from your probability distribution. Often samples are typically correlated with each other. So you don't do this just once. Typically you do it once, pull your samples and say, okay, this is from my probability distribution, but then you need to reevaluate and make some extra measurement. And you start with those points, but you have to run this algorithm long enough that they've all moved around sufficiently. Otherwise, you're just using the same points in the next step of your algorithm, which is introducing false correlations. And it's also kind of wasteful. You discard a lot of states that you don't use. So computationally, you're going to burn out a lot of resources unavoidably. Okay, so just to kind of recap so far, we've got this wave function that's a function of parameters. We've got some operator h that's describing our nuclear physics. And we want to understand, for this wave function, what's the value of our energy with this operator h, and then how do we minimize it. Taking the derivative of this expectation value as a function of the parameters turns out to be this. This is just the ratio rule of derivatives if you do this math. And you can write this a little more simply with another operator O. That's just the derivative of the wave function with respect to a parameter I. And this G we define as the gradients. You just compute this expectation value, the expectation value of the energy, and the expectation value of the derivative of your wave function. And that tells you the derivatives to update your wave function. Okay, so it's time for a short calculus interlude. In this algorithm, we've actually encountered a couple derivatives, and there's one more coming. So the Hamiltonian operator, if you recall, it had that gradient squared. That's a second-order derivative of some numerical function. And the gradient calculation itself requires a derivative of your trial function with respect to all the parameters. So you kind of have the choice, do you want to do these derivatives analytically, which if you have a simple function, like an exponential, that's easy, just go for it. You can do it numerically, that's always an option, but it's slow. Or you can use a machine learning framework that has automatic differentiation. So this was the sort of the new step that my collaborators and I added to this field, is you take a wave function and represent it as a neural network, and then you can take automatic differentiation for all your derivatives. There's some properties of physics that you have to apply here. So you can't just take ResNet as your trial wave function and hope that it works. Fermions, which is what protons and neutrons are, have this weird property that if you have decided that this is the set of fermions in my system, and you take any two and you switch them, your wave function has to change sign. It has to go from positive to negative, or it has to be 0. So if you're not allowed to switch them, then it's got to be 0, because 0 equals negative 0. The way we enforce this in our neural network, and this is a technique that's used in many body physics kind of in general, is called the Slater determinant. This is a little bit of a math explosion here of all these symbols. The short way to describe this is each of these rows across the top, the right-hand side of these little equations, this character, represents a single particle state. So that's saying this, I'm a proton, and I'm at this point. And all of the x's going down are all of your trial possibilities. So as an example, this is the deuteron. That is one proton, one neutron bound together. So your states are across the top, I'm a proton with spin up, and across the bottom, I'm a neutron with spin up. And that's the deuteron. You can only have a proton and a neutron each with spin up. But x here, which is your coordinates that you're sampling from with your metropolis walk, if you switch something, so say you started with a neutron and a proton, you can switch them. Maybe that's valid. You just have to change sign. You compute this matrix and then take the determinant of it. And notice that switching the particles mathematically equates to swapping 2 columns of your matrix. And if you swap 2 columns in a determinant, you flip sign. So this is how we encode this symmetry into a neural network. All of these columns are represented by neural networks in our algorithm. OK, more questions? Yes?
Yeah, I'm a little confused about how you represent your network. So for each column, you say a layer or?
Yeah, the question is how do I represent each neural network, right? Yeah. It's basically a multi-layered perceptron. And there's some extra constraints, which I think I talk about in the next slide. But each particle has just a few properties. It has a position, x, y, z, and it's either spin up or spin down. And it has this isospin property, spin up, spin down. And just in case you're not familiar with nuclear physics, isospin up can represent proton, and then isospin down represents neutron. So it's basically, if you flip that thing, you're just flipping proton to neutron. So I take a multi-layered perceptron that takes in x, y, z for each particle, has a couple layers, and spits out a value at the end, a single value that represents the wave function for that particular particle. So that is each of these rows. Here, that's a neural network. This is the same neural network, but you feed it in a different particle. Same neural network, feed it in a different particle. And then going down, this is the same particle into this network, same particle into a different neural network. So I have, for n particles, n neural networks here. And they're not particularly big. A couple layers, a couple hundred or 1,000 parameters per network. It's not the scale of millions of parameters.
Okay, so it's just
Yeah.
I see. And I don't understand.
Question over there?
Yeah, so it's about, I think, two slides back. Yeah, just to quickly, this quantity EL, what is, does it represent something physical? What is?
So physically, EL is actually pretty easy to understand if you have a particular point that you've sampled. So say I'm going to do my integral with 10,000 sample points. EL is the energy you compute for one particular point. So I sum up this value for every point that I've sampled from this walk. I compute this value, which is the Hamiltonian applied to that particular wave function, divided by the value of the wave function at that point. And that's kind of called the local energy. So that's what the L stands for, E local. And then I sum up all the local energies, and that's my total energy. More questions?
With the description of the neural network that you just made, the input variables are X and Y,
X, Y, Z,
X, Y, Z.
2 dimensions.
3 dimensions. So basically, the neural network is learning that spatial component and the arrangement
Right.
of particles that you have.
That's exactly right. And that's even the intuition for this matrix here. If you have enough particles that you don't fill up just a ground state shell. So for example, atomic physics, there's these electron shells. If you want to solve the atomic physics of something with more than one shell, these wave functions, or these neural networks, should converge to the right values for a particular shell. So this might be the first one, this is the second one, and then this is the next higher level. But that's the intuition, yes. Kyle?
Are all the networks the same size?
In this particular case, yes, they're all the same size.
So can you also represent excited states with this kind of?
Yes and no. You have to solve the ground state first. That variational principle only guarantees that the trial state is greater than or equal to the ground state energy. So an excited state, by definition, is higher than the ground state energy. If you try to solve the excited state, you're going to minimize to the ground state because that's the lower energy and that's where your minimization will take you. There are ways around it. If you solve the ground state, you can form, by construction, you take your solution, your wave function for the ground state, you can form another state on top of that that is basically removing the ground state from the algorithm. Everything you try to do to optimize to the ground state will just go to 0, and your energy won't go past the first excited state, in principle. There's some numerical errors. You no longer have the same guarantee that you're above. You might be a little bit below the first excited state, but you can kind of do it.
So in neural network representations, you may have two different neural networks. Okay, just just one single network, one set of neural network, and then you force automatically between the ground and excited states.
Yeah, if you wanted to map out the spectrum, you would need, I think of this as kind of one full neural network with many subcomponents. You would need multiple of those, one per state, if you wanted to get it right. And the convergence properties are not as guaranteed there, so that's a much harder problem.
Right,
Yes?
on the I think you call that thermalization, the rethermalization. How do you know when you've moved the point?
Great question. Typically, there's some calibration you do on this Metropolis MRT squared walk, and you measure what's called the acceptance. So when you have points that come out as a lower probability, there's some chance you might accept them and some chance you might reject them. When you have points that come out a higher probability, you always accept them. So you can take, for each step, on average, I accepted X points, and I had Y points total, and that becomes a fraction, 10% accepted, 90% accepted. You basically tune your kick size to adjust your acceptance to a right number, and there's some literature that suggests you don't want to be 90%, you don't want to be 10%. You want to be in the 25 to 75 range. And then you need to basically experimentally verify, if I run for 5 kicks, how correlated is everything? If I run for 500 kicks, how correlated is everything? And you want to run long enough that you break correlations, but short enough that you're not wasting all your computational time.
Okay, there's some boundary correlation with determinism.
Yeah, and it's not a science. That part is a little bit of a tuning art. That matrix I described is not the whole wave function. So there's another component that you need to be a general solution to this nuclear problem. And it has this exponential term. So this U we define as the correlator. It takes all of the positions at once with no respect to what particular particle they are. So this determinant of S gives you antisymmetry, which means that this function needs to be 100% symmetric under exchange of particles. We do this with the deep sets formalism. I don't know if anyone has encountered deep sets before, but it's basically two neural networks. You have this single component network, phi, and this general component network, rho. And there's a sum here. So for each particle, you apply phi individually, so it gets the three coordinates, x, y, z. You compute some latent space value. It doesn't have to be a single point in this case. It can be a pretty big space, 32, 64, whatever. And it's represented by a multi-layered perceptron. You compute the latent space for every particle, and you sum them all together. And that's called an order-destroying operation. So you can do a max pooling. You can do a summation. You can do anything that's symmetric under exchange of argument order. And then you apply another neural network, rho, which maps that latent space down to one value. And then you put an exponential term in. There's also some physical constraints that you have to do. We were talking about activation functions in the previous talk. You can't use ReLU here. And the reason for that is from quantum mechanics, a valid wave function has to be continuous and differentiable at all points. And ReLU is not differentiable at 0. So you actually have to use different activation functions like tanh, sigmoid, avoid ReLU. And you also have to worry about, for example, your metropolis walk. If you start with a wave function that could converge to the right state, but it's not bound, all of your kicks are going to end up pushing to weird spaces in the final answer that might be allowed by your initial wave function. So you have to include a confinement term in your wave function. And that's not a parameter. It's just this constant term, alpha. This is maybe a hyperparameter. It's not optimized. You just include, this is an exponential term. Remember, this u goes into e to the u, so this is e to the minus alpha r squared. It's a Gaussian confinement term. Everything flows to the middle by the probability from that, and the wave function pushes it back out. Okay, I'm not going to get into the details of this algorithm here, stochastic reconfiguration, but I can explain at a high level. If you have taken quantum mechanics, you know this. The wave function itself doesn't have the normalization necessarily built in. You have to divide by the normalization. So if you change the parameter of your wave function and it changes the values of your wave function, it also changes its integral. So just changing one small parameter doesn't give you the kick in the gradients that you expect. You get some second order effect coming from this normalization change. This algorithm called stochastic reconfiguration is a second order approach. It basically flattens the space of optimization so you don't have all of these weird effects. And you just compute this S matrix. And if you recall this O operator, that's the, for OM, that's the derivative of your wave function, the expectation value of it applied at some particular parameter n. So if you have 1,000 parameters in your neural network, this S matrix is an 1,000 by 1,000 matrix. We compute the inverse of this, which makes it a computationally challenging point, especially when you're doing machine learning. Oftentimes you're working on accelerators that are trying to push you towards 16-bit precision. If you try to invert this matrix in 16-bit precision, your algorithm will not converge. You do not get the right inversion answer. So we end up doing a lot of mixed precision where we'll do some components of our algorithm in 16-bit, 32-bit. This runs in 64-bit precision. And we also regularize it. So we just add the identity matrix along the diagonal with a small factor epsilon, which just ensures that this inversion will actually work. So this is the exact algorithm. If we have this S matrix exactly, we know what to do. Of course, we're computing this S matrix the same way we're computing the local energy for every point. It's with this approximation. So we don't have the exact matrix. So we have to balance this, this regularization term. The other part is this right here, OM, That's the Jacobian matrix of your network. So if you ever have a neural network and you want to take the Jacobian of it, that actually turns out to be a tricky thing to do with some of the deep learning frameworks. All right, I can go through the summary quickly. I'm not holding you up for lunch yet. Basically, you start with a number of points, pick them randomly, go through this algorithm where you thermalize them to get to your probability distribution. From there, you calculate all your observable quantities, the local energy, its derivatives, and this reconfiguration matrix S. You accumulate those observables a bunch of times, so just one measurement isn't often enough. If you had a GPU with a terabyte of memory, you could probably do this in one pass, but we don't, so we usually do this a bunch of times. We'll do this initial equilibration for a long time with our algorithm, and then we make a measurement of everything, the derivatives, the matrix. Then we do a decorrelation step, so we remove we do this algorithm again where we're walking this Metropolis algorithm for a while, remove correlations, measure again, and do this until you're pretty confident that you have a good approximation of the gradients. Then you update your wave function parameters with this thing. And this is not quite your traditional gradient descent because it's got this S inverse matrix in it. This is the stochastic reconfiguration algorithm. It's a second order gradient descent. A word about computational efficiency, since this is ATPESC. You could implement this in lots of deep learning frameworks. We've tried it in 3, not there, but 3 deep learning frameworks. So we tried it in TensorFlow, Torch, JAX. JAX is the clear winner. So if you're doing anything with weird derivatives, JAX is just awesome. Torch is imperative. What that means is each time you call Torch in Python, it's going to evaluate that. With some operations, it will return to Python and let you move forward and eventually synchronize. But this walk algorithm is just too slow. Torch, it's a couple steps, but you do it thousands of times. And PyTorch just gets hung up there. libtorch is better. That's the C++ bindings. But that has big concurrency issues when you try to compute your Jacobian. Torch is really great when each operation on a GPU is big. So convolutional neural networks in PyTorch are just awesome. When there's a lot of small ops, Torch just falls over. TensorFlow is better. But if you're familiar with TensorFlow, you know they do this graph compilation stage. And that actually will time out for bigger nuclei. Because of the n squared component of some of these algorithms, it's compiling a graph n squared times, and it will not finish compiling. TensorFlow does have really excellent scaling properties, though. We've scaled out to a large number of GPUs wonderfully. JAX, I don't need to say too much more about this, but JAX works really well for this algorithm because you can get all of these weird derivatives. All right, so I can't do this talk without showing you some of the results. So here's the deuteron. This dashed line along the bottom is the exact energy of this solution, of this Hamiltonian. Deuteron only has 2 particles, so we can solve this exactly with traditional theory methods. Here's our artificial neural networks. This is a hyperparameter for the Hamiltonian that's basically just how strongly are we binding things artificially to start. It converges to the same energy, and our neural network just gets spot on, right down to the binding energy of the deuteron. Here's a table going up to A equals 6, where A is the number of nucleons. Since this table has been made, we've actually reached 12 nucleons, and we're going up even higher. So we can get down to lithium, beating state-of-the-art non-neural network techniques. It's also not just good for the energy. So here is helium. We solve this variational problem with a neural network to get the binding state of helium. But then we step back and look at our network and calculate the probability distribution to find a nucleon at some distance r from the center of mass. That's an experimental quantity. That's also something you can solve exactly for helium. So this blue is the exact solution. And our neural network gets it right over 4 orders of magnitude. So if you zoom in down here, down to 10 to the minus 4 versus 1.2, the neural network knows exactly what the right probability distribution is. There's some optimization tricks we play with this. So I talked about a couple hyperparameters. One of them I don't think I mentioned in detail is this learning rate. Here it's written eta. Later I write it delta, but it's the same thing. But it's basically your learning rate. And then there was that component in your matrix inversion to regularize it so you can actually invert the matrix. Instead of picking these parameters by hand, we actually build this into the algorithm, so it's an adaptive search. You can see here, if I just do this flat algorithm where I pick 2 of them and take the best one, how quickly does it converge? That's the green line. And this, I believe, was the deuteron. It gets to the right energy eventually. If I do that epsilon term, and when it comes time to invert the matrix, I pick a bunch of epsilons, try them all, figure out what the next energy is going to be. And because the weight updates are small, I can use the same parameters to calculate what the next energy will be after I update the network. I pick the smallest one and make that update, and it converges faster. And here's just picking the learning rate using the same technique. So figure out, here's my gradients. If I take a step this far, what's the next energy? This far, this far, this far. And it's basically mapping out the space along that direction, go to the lowest point on that space, and it will converge to the right answer much faster. And these have a marginal computational cost additionally. The adaptive learning rate, ADA here, is a little bit slower. Doing the matrix inversion with an adaptive part is a little bit slower still, and that's because you have to invert a bunch of times. It's also scalable, so this was on Theta GPU. We're working on running it even bigger on Polaris, but we have basically ideal weak scaling up to all of Theta GPU. And a lot of that's because this Metropolis algorithm doesn't care what GPU you're on. You can just split up your particles onto all of the GPUs and run them forward, and that dominates your computational time anyways, so you can go as big as you want effectively. This is ongoing, so our intention over the next year or so is to solve calcium, which is an even bigger nucleus. And for that, we're targeting Polaris. I don't know if I can post slides from ATPESC, hopefully yes. But if you Google this repository, Nuclear Physics with Machine Learning, you'll find all our code open source. And there's also some tutorials on these numerical techniques, as well as lectures posted there with a lot more detail on the statistics and the algorithms. And if you are interested, you can do some of these hands-on exercises in TensorFlow. And we solve the hydrogen atom in a notebook there. OK, so that's all I have to say. Questions?
Just a question on like the physics. Assume you represent the exact wave function as a product of single particle functions, a neutron.
It's not a product of single particle functions, so it's two pieces. It's this S matrix, which is a determinant of single particle functions, which is not the same as the product mathematically. And then there's this correlator part, which is absolutely not single particle wave functions.
Right. So I guess my question is, like for like electronic structure theory, we do something very similar, but we're just considering explicitly electrons.
Mm-hmm.
And so here in your determinant, you have functions of protons and neutrons.
Mm-hmm.
Is there a correlation between electrons and neutrons?
Between protons and neutrons?
Yeah, like the electron, neutron, both have the Coulombic correlation.
Yes.
You see that between a proton and a neutron.
Yes, you do. That's all built into, and I didn't talk about it much, but right here, I talked a lot about this term, how you compute it, but this term here, V, has that built in. So that R is a generalized coordinate. It's not just XYZ, but it's XYZ spin, isospin. And isospin is differentiating proton-neutron. So yes, your potential between two protons and two neutrons is different. And this includes Coulomb interactions and weak interactions and strong interactions and everything.
Oh, yeah, okay. So you have those other.
Yeah.
That's weird.
Great. Yeah, great question.
Thank you.
More questions?
I think going back to when you do a spectral determinant, and when you're working with electron determinant, we usually extend a basis with different L's to get all the configuration in the. This is from the point of view of full configuration interaction. In your determinant, how large, or do you use higher angular momentum function? Because something I noticed is that the atoms or the system that you show are actually S symmetry. What happens if you go to carbon instead of calcium? Calcium again is also going to be L equals 0. But what will happen if you have a degenerate of insurance?
Yeah, great question. I didn't talk about this. We actually just posted a paper on the archive this summer. It's submitted to a journal. So we use this technique called hidden fermions, which I think is the same thing. So this Slater determinant becomes much bigger than just your number of particles. So if you have n particles, this one is written as n by n, and we extend it. So n plus x to n plus x, where those are considered hidden states, and they play into the wave function. But they're not necessarily the states you observe. And I think the whole point is to map out more of this complex space.
But how do you know that you are doing the L as J correct copy and you are really seeing it?
We don't know exactly, except that each state is a neural network. And if you're going to get to the ground state energy, then you have to get the right states.
Also, I suppose that you use a Gaussian-based functions to determine how. Just out of curiosity, have you tried Slater type?
No, and I should defer you because you're starting to ask me physics questions, and I'm not the theorist here. So I keep up with the theorist. He comes and says, here's our Hamiltonian, and I can scale it out on Polaris. But if you want to know more about the physics, I can put you in touch with some of my colleagues. Yeah, sure.
So for the random walk that you do, I mean, it must be sampled from a distribution, right? So normally, I'm just curious, when you sample something from a distribution, you have this inverse correlation matrices that's being used kind of hidden, which you don't see normally when we implement random walk on PyTorch or something. So I was curious, how did you scale that inverse version of that matrix? Unless it's really small, I could see it being fit in the GPU memory, but if that matrix is big.
So you're asking about when I take one particle to the next state, how do I draw the update? It's sampled from a Gaussian.
Or maybe it's that Gaussian matrix. There must be correlation matrix, right, for the Gaussian? Or
There probably is. I haven't thought about this in detail. This is a good question. We're just pulling from uniform distributions and updating the keys each time, the random seeds each time. That's a good question. I don't have the answer for you, so I'm not going to BS it. But thanks for the good question.
I have one other small question. So in the next slide, for that, the first exponential term, so that u of whatever the r vectors are, is that u bounded? Because if it's not bounded, it could the error could the phi could blow up, right, pretty easily.
Yes. Yes and no. Phi is not bounded, but we include an artificial binding term. So it's this alpha sum over r squared. And that's not a physical term that shows up in the end of the wave function. That keeps everything bounded during your walk. And the neural networks will actually learn to exactly compensate for this. So no matter what alpha you pick, as long as it's relatively in the right range, like 0.1 to 1, you will get the right spatial distribution of your particles, like shown here. So your network is artificially bounded and will compensate for it exactly.
So when you compare, how long it takes to run your approach versus the standard approach?
Computationally, we're competitive at small nuclei. At large nuclei, the traditional approaches will scale computationally as 2 to the a, where a is the number of nucleons, and we scale as a cubed. So as soon as you're getting to bigger nuclei, those ones are not feasible, and we can actually do it. So it will take a supercomputer to do something like Argonne. We're targeting a lot of nuclei relevant for experimental physics, so argon, xenon, oxygen. Yeah, but we can actually do some of them that are not feasible otherwise.
So A to the cube is a typical quantum Monte Carlo scaling.
What's that?
So you said it scales A to the cube.
Yes.
That's the typical quantum Monte Carlo scaling.
Are you asking or telling me?
I mean, as
Asking. Yeah.
exponential in number of particles, and your network is trying to, for example, just to.
It's this right here, this trial wave function. If you come up with something clever, you can go faster. If you want to be arbitrarily general without machine learning, you end up with something I believe is like 2 to the A. And that, I don't know the theoretical details of all of these traditional methods. That's not my expertise. So I won't try not to say wrong things.
The color scales enter the cube.
Yeah.
And seems like neural network does not include that scale, but it scales much better than the traditional way we do.
That's the goal. Yeah, and to get better energies with better trial states.
So if I understood it correctly, the algorithm mostly relies on replacing the wave function of individual particles by neural network, correct?
That's right.
So I just wonder, I mean, neural networks approximate basic arbitrary functions, and you can say that a single hidden layer is enough, but there's no upper bound on how many neurons you need, right?
Mm-hmm.
So I was just wondering, have you experimented with the number of neurons per layer and the number of layers? Because ultimately, if the neural network cannot describe the wave function accurately enough, then that will not work, right?
That's right.
So have you any experience with how many layers you need and how many neurons you need?
Yeah, and it's not as many as you think. So most of these, they're all multi-layered perceptrons, and they show up in a couple spots. Typically, it's like 4 layers with maybe 32 activations per layer. The total number of parameters comes out less than 20,000, which is a necessary step because remember, we're building this matrix and we have to invert it. So if we went to million by a million parameter matrices, we're going to spend all our time doing matrix inversions with this particular algorithm. Now, I understand there's some other algorithms we can try to get around that, and I don't want to talk about the details of that yet. But to answer your question, the order of magnitude number of parameters, 20,000, maybe 4 layers per network. Guess enough. If you go down to 2 layers and 8 activations per layer, you will not solve it. Thank you all for your attention and questions.